Hi everyone, welcome to my AE2610 digital sampling lab. This is my slide report on the impact of height and container on volume generation when pouring water by me, Timothy Young, and my lab is AO2Y. So first things first, let's start off with prior to week 2 track data and classification. Here you can see I've labeled the track number, the type of signal it corresponds to, the peak principal frequency for each signal, and other peak frequencies for each signal. Some notes I want to make about each some of the signals is that the square wave and the ramping wave both had peak frequencies, other peak frequencies of every 1,000 hertz from 0 to 10,000 hertz. For the square wave specifically, the second highest peak was at 3,000 hertz, and for the ramping wave, the second highest peak was at 2,000 hertz. And these both had lots of peak frequencies that were not 1,000 and pretty much kept repeating in intervals of 1,000. And so moving on, for tracks 7 and 8, both are white noise sine waves, but track 8 was significantly more noisier than track 7, meaning that there was more white noise with track 8 than track 7. And so let's move on to my experimental motivations and goals. My experiment observed how much volume is generated when pouring water into different containers at different heights, and I was pretty much inspired by this when I was pouring coffee one morning a few days ago, and I was like, I wonder how bartenders make it so flashy when they pour water from really high up and it makes like a decently loud sound. And so, there's a sort of showmanship that goes into bartending, and pouring drinks from varying heights is part of that. And pouring at varying heights produces varying sounds, and I was curious on the relationship between the height and the sound. Thus, with this experiment, I want to see how loud pouring water was from a tall height is compared to pouring it normally, like on the lid of a cup. So moving on to experimental procedure, these are my experiment parameters here. The containers were a plastic cup and a porcelain bowl. The plastic cup was 4.7 inches tall and 4 inches in diameter, and the porcelain bowl was 2.25 inches tall and 8.5 inches in diameter. The pour heights were 0, 2, 4, and 6 inches in increments of 2, and the mic was 6.5 inches up from the ground, which meant that it was 1.75 inches from the top of the plastic cup and 4.25 inches from the top of the porcelain bowl. Data acquisition wise, the gate, I had a pour gauge set up by making tick marks from 0 to 6 inches drawn on a standing paper towel, and this would help guide me as I poured the water manually into each container. The actual setup included me putting the mic next to each container, and my mic would be taped to my water bottle, 6.5 inches up the water bottle, and it would pick up the sound as I poured water into the container from certain heights highlighted by the pour gauges, and these pour gauges help me pour water from the heights relative to the top of each container. So this would be for the cup, and this would be for the bowl. And data-wise, I used GTA Simple DAC to record the time histories picked up by the mic as water was poured from the different heights. And so here are the results. I decided to plot max volume versus height for the cup and max volume versus height for the bowl. And so as you can see here, in general, as you go up in height from the top of the container, you reach more higher and higher max volumes for the cup. Whereas for the bowl, as you go higher in height, there's not much difference for max volume. In fact, it stayed pretty consistent. The slope is pretty much 0. Whereas for the cup graph, you can tell that it's a positive correlation between the two variables. Moving on to success criteria and conclusions, my original hypothesis was that pouring the water at higher heights would produce more sound, and pouring the water into the cup would produce more sound than pouring it into a bowl. And this was generally true for the cup, anyways, because the cup was tighter than the bowl. My theory was that the sound waves would bounce off the cup more and be more concentrated to be picked up by the mic, whereas the bowl was way wider and sound waves could kind of bounce off the bowl in any sort of direction compared to the cup. And so my hypothesis did generally hold up when pouring water into the cup. As you can see, there's a general positive correlation between height from the top of the container and max volume. But I did not expect that the height of the water poured had pretty much no effect on the volume for the bowl. And as you can see here, the graph is pretty much straight. Pretty much no correlation between the two variables here. And so here are some complications and mitigation strategies that popped up during the experiment. One big complication was pouring the water with a constant speed. I was manually pouring the water, which made it very prone to human error. I felt like some of the runs I was doing, I was pouring the water a bit too fast, maybe I was pouring the water a bit too slow, and ultimately this would lead to inconsistencies in the time history graphs. So ideally, if I had some sort of device like a burette that could stand and pour water out at adjustable heights and at a constant speed, the experiment could have been much more consistent, but I don't have access to a burette. And next, there was a lot of background noise when I was doing the experiment. This background noise happened before, after, and during the pouring, which made deceiving volume spikes that made it hard to analyze the graphs in post. And miscellaneous background noises include just moving my mouse around and clicking, or my desk and chair creaking as I moved. And so a good example of this is this spike here and here. The spikes at the beginning and the ends for the time history for the 6-inch pour into the bowl and the 6-inch pour into the cup. These mainly came from me just clicking and moving my mouse around, trying to start and stop the time histories, which made these deceiving spikes that I had to pretty much ignore. And this would have been mitigated by having the mic closer or maybe even inside the container where the water was pouring, but our mics aren't waterproof. And so here are my image sources, and thanks for watching. Wahoo!